Okay, class. This is part one of the little acids and base section that we did the other day. You might recall that I forgot to record it, so hence I'm redoing it. Okay, so the first section we're going to be talking about is going to be acids and bases, and this is the Bronsted-Lowry version of things. We'll get into the Lewis acids and bases on Tuesday. So there are two broad definitions, the first being the Bronsted-Lowry, which we'll talk about today, the second being Lewis. And technically, the Bronsted-Lowry is a subset of Lewis acids and bases. So everything that we're talking about today can be basically moved under the umbrella of the Lewis acids and bases a bit later on, and I'll show you how that happens. But for this, the thing to remember for the Bronsted-Lowry acid definition, that's a substance that donates hydrogen ion, so H+. Whereas a Bronsted-Lowry base is a substance that accepts H+. So one will be, and remember, hydrogen ion is basically a proton. So one will be a proton donor, the acid will be a proton donor, and the base will be a proton acceptor. And the second thing to remember from when we're doing these all of these reactions, you're going to have an acid base, conjugate acid, conjugate base pair. So if we look at both sides of the equation, what we're going to see is that on one side there's going to be an acid and a base, and on the other side, the product side, there will be a conjugate acid and a conjugate base. And for all of these reactions, what we're going to want to do is generate the weakest acid and the weakest base. So the direction of this equilibrium of these arrows is going to be dependent upon the acids and base strengths of the conjugate acid versus the acid, or the conjugate base versus the base. So it's an equilibrium, and the ability of, say, the acid or the conjugate acid to donate its proton is going to dictate which direction this reaction goes. So in this example here, we've got hydrogen chloride. So, and then this is going to be the acid. The base is water. So this would happen when you bubble hydrogen chloride into water to make hydrochloric acid. Remember, this is following our rules about negative going to positive. So chlorine hydrogen bond, this is polarized. Chlorine is more electronegative, so the H end will be the delta plus. And here we've got our negative electrons going to the partial positive charge. So negative goes to positive, and then these electrons are going to move on to the more electronegative atom, chlorine, to make chloride ion. And then we've got H3O plus as the conjugate acid. So all of these reactions will be able to draw little curved arrows where the base is going to be picking off a proton, and then the electrons in the whatever atom this is, hydrogen bond, are going to move towards that atom, whatever it happens to be. So that it's a repeating reaction over and over and over again. Base grabs proton, electrons in the proton, in this case chlorine bond, move towards the chlorine, the more electronegative atom. All right. So back in general chemistry, we would have had we would have talked about the equilibrium constant. So if you've got reactants and products, the K equilibrium, and if this is in an equilibrium, you put the products on the top and the starting materials on the bottom. And the higher the number, the more the reaction would go towards the products. Because if you're dividing by a small number and you get a bigger number, this number will get larger if it's going towards the products, and it'll become a fraction if it's going toward if the equilibrium rests with the starting materials. Now, so if we've got some generic acid, HA, and water, lone pair is going to grab that H to make H3O plus, and we're going to have our conjugate base here, A minus. The equilibrium constant would look like this. But for acids when we're talking about Bronsted-Lowry acids, what we use is the acid constant, which is the equilibrium constant multiplied by the concentration of water. And so we're basically removing the water from this expression by multiplying both sides by the concentration of water. And that gives us an expression which looks like this. So conjugate acid, conjugate base over the acid, I guess. And so this gives us a Ka value. So in this sense, if this is a very strong acid, this number, the Ka would be very big. And if it was a weak acid, the Ka would be very small. Now, it turns out that the range for the acid constant is absolutely enormous. So the strongest acids are like 10 to the 15, and the weakest are 10 to the minus 60 or so. So because the scales are so ginormous, what's used is they use the logarithmic scale to give it to some numbers that we can actually work with. So if you take minus the log of the Ka, this will give us the pKa, just similar when we're talking about pH, and that's, talking about pH. And so when you do the minus the log of the Ka, what happens is the strongest acids have got low pKa values, and the weakest acids have the highest pKa values. And the range is roughly between minus 10, the strongest acids are minus 10, to the weakest being somewhere at around 50. So low pKa values, strong acids, high pKa values, weak acids. So if we had a strong acid and it was reacting with the base, the reaction would proceed as follows. The base lone pairs would grab that proton, electrons move on to the atom, whatever happens to be. This would be the conjugate base, and then the protonated base becomes the conjugate acid. So for strong acids, this reaction is in this direction, and you're going to generate a weak conjugate base. So all strong acids readily lose their proton. So the strong acid is going to become the conjugate base. And if it's a strong acid, the conjugate base is going to be exceedingly weak. Now, conversely, if you've got a weak acid, so a substance that doesn't want to lose this proton at all, doesn't want to do it, but if it does, they have a corresponding very strong conjugate base. So this reaction would be in exactly the opposite direction. So if you had a strong conjugate base, this would grab a proton, generate this would be a weak base over here, and you would form a weak acid. So remember, you always want to be generating a weak acid or a weak base. So that's the direction that the equilibriums are going to lie. So the key point is that strong acids are going to generate exceedingly weak conjugate bases, and that's why they give up the protons so easily, whereas weak acids resist losing protons because it generates a strong base. So if you want to remove this proton, you're going to have to use a base which is stronger than this base over here. That's the rule, right? Okay, so now the nice thing is that you can use pKa values to predict if you draw out a reaction like I've drawn here, if it's going to shift towards the products or if it's actually going to shift back towards the starting materials. So on Moodle, I will have posted at least 2 pKa tables. Your textbook's got pKa tables. Typically, the pKa tables in textbooks are pretty generic. There's not a whole lot of different molecules on them. But you can, the ones I posted on Moodle have got a bit more like different functional groups, that type of stuff. And you get a larger glimpse at the varying acid strengths of different types of compounds. But remember, pKa's, weak acids have high pKa values. So what we want to do is that if there's a reaction in such a fashion like this, we want to see which side of the equation has got the highest pKa value, because the reaction is always going to go towards the highest pKa value, because the highest pKa is the weakest acid. So it's always going to travel in the direction of highest value. So in this case, this example here, we've got HF, hydrogen fluoride, we've got hydroxide, and this is going to come grab that proton, and we're going to be generating water and fluoride ion. And so if we want to compare the two, if I hadn't drawn the acid-base conjugate base here, if we had to look at these two things, the two substances in this case, the water and the HF are the two substances which actually have the protons, right? On this fluoride and the hydroxide, so this will be the acid and the conjugate acid, and the base will have the lone pairs, in this case with negative charges to grab the proton with. So we would look up on our table, water's got a pKa around 15.7. HF has got a pKa just under 4. This is the weaker acid, so the reaction is going to travel in this direction. I've got another example on the next page with some substances which you probably haven't seen too often. So this substance over here is a 1,2,3-diketone. That's a generic sort of name for it. These protons here can be removed, and you notice the pKa of this acid's around 9. Here we've got a base, NH2 minus, and I've drawn the equilibrium showing the direction of this reaction. So here's the conjugate base, which acid becomes the conjugate base. It's got a negative charge. The conjugate acid comes from the base. It's now neutral because it's been protonated, but you notice the overall charge minus on this side, minus on this side. But you notice the pKa of the conjugate acid here is 38. This value is far higher than this value. And so this reaction is going to go towards the weakest acid, which has got the highest pKa value. So this will go in this direction. So if you've got some pKa tables, it's always good to take some time to, you certainly don't need to memorize them, but just look at different functional groups and see what the pKa's are. And then you can sort of make a little, like a tree, like a scale of what's a weak acid, what's a strong acid. So strong acids will generate weak conjugate bases. Weak acids, conversely, would generate strong conjugate bases. So this reaction would go the opposite direction. Strong bases generate weak conjugate acids, and weak bases would generate very strong conjugate acids. So this would, again, be in the reverse direction. So in all of our acid-base reactions, you want to generate the weakest acids and the weakest bases. And so with Bronsted-Lowry, the acid is going to become the conjugate base, and the base is going to become the conjugate acid. Okay, now the other nice thing about pKa tables is that you can determine what is the strongest base using those same numbers. There is such a thing as a pKb, but it's not used as much because, and you would have done that when you were doing Gen Chem, the acid-base section with Dr. Chen. The so here we've got two different functional groups, an alkyne, carbon-carbon triple bond, got a proton here. We've got an amine. And if both of these are protonated, the pKa of acetylene is 25, the pKa of ammonia is 38. You will notice that this number, 38, is higher than 25. So NH3 is a weaker acid, right? So, because it's got a higher pKa value. So NH3 is a weaker acid. So remember, weak acids would generate strong bases. So if this is the weaker acid, that means that the conjugate base over here, NH2 minus, is a stronger base than when acetylene's been deprotonated, because it comes from a weaker acid. These values show that NH3 is a weaker acid than acetylene. So if you look at the conjugate, if you look at the pKa and you determine, and you're comparing two substances, they have to be protonated, of course, because that's where the pKa would come from. Oh, this is a higher number, so it's a weaker acid. That means that its conjugate base has to be stronger. And so not only can pKa values be used to determine which is the strongest acid, they can also be used to determine which is the strongest base by once you've deprotonated them. Substances with high pKa values, the corresponding conjugate base will be stronger because it's coming from a weaker acid. Yeah, so that's basically, that's how, so another reason to look at your pKa tables, just to get the flavor of where things fall. So predicting acid strength. pKa tables, of course, are very useful. And so, as I said, go through and look at them. See what the various functional groups are. And it's going to give you some glimpses into, you might look at something and say, why is that so acidic, or why is that not acidic? The next part of the class, which we're going to do, is that when we can look at a molecular structure and we can follow a number of simple rules, and it's going to give us a really good idea about what's a good acid and what's not a good acid. And so that's the second part of this lecture. Great. Okay, so we will end it there.